This video, along with all course content, including laboratory and hands-on activities, were developed by Andrew S. Heinz, PhD, and are copyrighted 2016, 2018, and 2020. All rights reserved. The student's course handbook serves as a guide and as a resource to the student throughout the course. It contains the sample problems done during class, laboratory activities, and practice problems to develop knowledge outside of the classroom. It is available on Amazon. Hello everyone, and welcome to Introduction to Basic Concepts Engineering. This is the second part of our Launch the Rocket lab, where we are going to be looking at how to solve this problem via spreadsheets. But before we get into that, make sure to check out the first video if you have not already. But what I want to do real quick is just a quick reminder of the equations that we're going to be using in launching our rocket. So what does it take to lift our rocket? Remember, we know that work equals force times distance. We know that force equals mass times acceleration. So what that really boils down to, once we combine those two, is that it's going to be the mass of the rocket times gravity times the height that we need to lift the rocket will be the total amount of work that we need to put in to lift it that particular height. To that end, we know that we need fuel. We need to burn fuel to lift our rocket. The energy that we need, the work that we need, that's what we just solved before, we need to produce energy equal to the work required to lift the rocket by burning our fuel. So the energy per mass of fuel times the mass of fuel gives us the total amount of energy needed. We know, of course, that as we add more and more fuel to the rocket, we actually have to put energy into lifting that rocket. So that will be the objective today, is finding exactly that right sweet spot, how much fuel we need to add to get our rocket to exactly the height that we want it to be at. Alright, so let's go ahead and get into our spreadsheet. All right, guys, so this is our spreadsheet. Of course, it's a blank document, and this is what we're going to start building. So I do want to run through a few things in Excel real quick. The first thing to note is that we are using Excel for our spreadsheet program. This will work very similarly to Google Documents or anything like that. That is also a spreadsheet program. There may be a few differences. See up here, there's formulas. There's some built-in formulas in Excel. These may fundamentally be different depending on the program that you're using. But the actual way that we're going to be building the sheet out and the way that we're going to be doing our formula and equation entry will work the same regardless of what type of spreadsheet you're using. All right, so let's remember what we're trying to do here with our rocket is we are trying to lift it to a certain height. How we're functionally going to do this here is we are going to, instead of looking at how high and how far we need to make our rocket go, what we're going to do is break that down into little tiny steps. So what we're going to do is we're just going to start in cell A1. We're going to put D height. Okay, and that will be, of course, in, let's just call it meters, so we keep our units. Remember, we need to keep track of our units. So what this is going to, let's go ahead and just set it to 1. What this D height or delta height means is this is the increment that we're going to look at. So what it means is each increment is, in this case of 1 meter, means that we are going to look at the increment of lifting the rocket 1 meter. Okay. Next, what else do we need to know? We need to know our rocket mass, right? How heavy our rocket is, because of course that fits into how much energy we need. Now, the weight value or the mass value that I've decided to use is 2 million. That's 2 million kilograms. The reason is that is roughly the weight or the mass, I should say, of the space shuttle, the NASA space shuttle. So I figured that was a good starting point. Right, next, remember our fuel, we need to know how much fuel we're going to burn, and that's dependent upon the energy density of the fuel. So I went ahead and looked up a BP rocket fuel. So let's go fuel energy density, and let's go ahead and make ourselves just a little bigger so we can read it. And that is going to be in joules per kilogram. Now, I looked up the BP rocket fuel, and it is 44.65 megajoules per kilogram. So what we want to do is we want to go up to our formula bar up here. So it is 44.65. Now that's megajoules. So what do we need to do? We need to actually multiply it by, what's a mega? 1 million. So 1, 2, 3, 4, 5, 6. Okay, so we've got equals 44.5 times 1 million, and that gives us the amount of joules per burned kilogram of rocket fuel. That's pretty high, but again, our rocket's going to be pretty heavy that we have to lift. All right, next, and this is going to be the cell that we end up changing, but this will be initial mass of fuel. Okay, so let's go ahead and again, that'll be in kilograms to keep our weight consistent. So to this end, we will have to basically start with something. We don't want to start with 0 because if we have 0 fuel in our rocket, how high is our rocket going to go? Nowhere. So let's just go ahead and just for a starting point, give our rocket 1,000 kilograms. All right, so this gives us the starting point for our spreadsheet. So what I like to do is I like to go down to cell 10 before I start building. And let's go ahead and start doing our labels. So we're going to look at the height of the rocket. And that's in meters. So we'll do this to note that it's in meters so we can keep track. Okay, next, what do we need to know? We need to know the total mass of the rocket, because the total mass of the rocket won't just simply be the rocket weight, it will also be the mass of the fuel. So total mass of rocket, and that will be in kilograms. Make sure to note that. All right, next, we need to know how much energy is going to be required to lift the rocket. And that will be, of course, in joules, or energy unit. Okay, so there are a couple more labels we need to add, but let's go ahead and start building our sheet. So what is the initial height of our rocket? It is 0 meters. It's on the ground. Okay, what is the total mass of our rocket? Total mass of our rocket is this, right, which is the actual rocket mass, plus the initial mass of fuel. So what we're going to do for our formula here is we're going to go equals, and then we can actually just destination this cell right here, reference the cell, add a plus sign, and then we can reference the B4, which is the initial mass of fuel. All right, so given this is our formula, what we're going to be doing over the course of this is our plan is to build our function, and then what we're going to do is we're going to do what's called a drag down. So a drag down can be accomplished by picking on this little box here and literally just dragging it down. And what the spreadsheet will do for us is it will automatically propagate that equation down and below. However, what we see here is the spreadsheet freaks out. That's right, so again, let's look here. So this says B2 plus B4, okay, rocket mass plus initial mass of fuel. But when you do the drag down, what happens is it actually propagates trying to link above. So you notice that when we did the drag down, instead of saying B2, B4, now it says B3, B5, okay? So what we need to actually do here is we can go in and we can do what's called a locked cell. So if you put a $ in front of putting it in front of the column locks the column. If you're dragging it side to side, putting it in front of the number locks it. And if you are dragging it from top to bottom, the row that is. So let's put it on both. And now these cells will be locked as the formula drags. So let's do it again. Let's do our drag down. And there you go. Now it is the same all the way down. Okay. Let's go ahead and delete this. All right. So the height of the rocket is 0. Our D height is 1, right? So at this line, what this means is at this line, we're going from 0 to 1. We're raising our rocket by 1 meter from 0 to 1. So how much energy is going to be required to lift the rocket? Well, remember our equation. It's going to equal mass times gravity times D, which is distance. So what's our mass? Well, we want the mass of the rocket here. We do not want the initial here, right? Because what we're going to do is we want to reference this cell. So we're going to go B11 plus, times 9.8, which is gravity, times, what do we think? Times our delta height. But now again, what do we need to do? We need to lock this cell to make sure that it's constantly referencing that cell even when you drag it down. All right, very cool. So what this is telling us now is with our rocket of roughly 2,100,000, it's going to take us that many joules to lift the rocket. So now what do we need to do? We need to determine how much energy we need to burn, or how much fuel we need to burn to create that energy. So let's put in, so we know energy required, Now we need to know fuel consumed, and that will be, of course, in kilograms. All right, so what do we think the formula would be here? Well, very simply, it would be equals, this is, so remember our units here are joules per kilogram, and we need a kilogram output. This is in joules, which means we need to divide it. So we're going to reference this cell, and we are not locking this because we do want it to be this cell, divided by the energy density. We do need to lock that, of course. All right, so what that is telling us is that in order to lift our rocket by 1 meter from 0 to 1, we are going to consume 0.439 roughly kilograms of fuel. All right, so now what I want to know, and what we want to know, is we want to be able to keep track of how much fuel is remaining in our tank. So let's do this. Let's go fuel remaining. That will also be in kilograms. Now, how would we do this? We simply say, all right, this is how much was consumed. We know what we started with. So we're going to go this, and we'll lock that cell because that one always stays the same. Minus the amount consumed. All right, great. So now we start with 100, we use 0.439, and we're left with 99.56. Right, now the last column we want, and this one's important, not like all these aren't important, but this one is also important. We want to know the new mass of the rocket. That will also be in kilograms. And this one, very simply, to get the new mass of the rocket, we take the total mass of the rocket at the start, minus the amount of fuel consumed. Actually, let's do it this way. Let's actually do with the amount of fuel remaining. Oops, B11 plus the amount of fuel remaining. And then let's actually do this instead. Let's go initial rocket mass. So what we're doing here is we're taking the initial mass of the rocket mass, because the mass of the rocket itself isn't going to change. So we're going to look at the mass of the rocket plus the remaining fuel will give us the new mass of the rocket. Okay, so B, $2, locked cell, plus E11, the changing fuel remaining, will give us our answer there, right? So again, it makes sense. We went from 2,100,000 to what we consumed, and now it's less. Right, so now let's go to our next row. And what's cool is all we need to do now is build this next row, and then we can drag it down to as far as we want. All right, so for the new height of the rocket, what do? We know we're at 1. So we could plug in 1, and then go 2 and 3. But instead, we want to build a program that will let us, if we want to, come in and change this height. So what we're going to do is we're going to reference cell above plus the delta height. And we'll want to lock that so it doesn't get dragged down. All right, so now we're at 1, and then a K, right, as we drag this down, it will continue to populate for us, okay? Right, the mass of the rocket now, what is the total mass of the rocket? It simply equals our previous line. All right, so what we're doing here is we are making calculation on how far it takes to go from 0 to 1, using that as the basis from 1 to 2, and so on, and so on, and so on. Now, the energy required to lift the rocket is just this cell times gravity times our change. So this one actually we can just drag down. It stays the same because the formula, of course, is solid and it's referencing the cell, no problem. The fuel consumed also is referencing the cell, so we can drag this guy down. Fuel remaining, however, is going to be the above cell, right? Because this is how much fuel we had left, minus how much fuel we consumed. All right, so now we have that built. And then what is our new mass of the rocket? New mass of the rocket is going to be, actually we can do a drag down there because what we're looking at is the rocket mass plus the fuel remaining. So if we drag this down, we will see that our rocket now weighs less. All right, so now what we want to do, so a mistake many will make is they'll select both of these and drag down. We don't want to do that because remember, some of these cells have different equations. So what we're going to do is we're going to select just these cells and go to this little guy here. And we are going to drag down until we get to, let's say, 1,000. Okay, so we need to go to what, like 1,010. I think it's 1,011. Let's see if we get there. All right, yep, so 1,011 puts us at 1,000 meters high. All right, so We lost, of course, this part, so let's do this. Let's go up to our View tab, and we can do this real cool thing called Freeze Panes. Okay, and what we've done, whoops, I clicked the wrong one, I'm sorry. Unfreeze Panes, now we go Freeze Panes, and what this does now is it leaves this row as we scroll down, right? So wherever you put it, wherever you put your cursor, whichever row, you go freeze. So right now it would unfreeze it if we clicked it, but you just go Freeze Panes, and it will leave this all to the top, but it allows us to scroll down through the sheet and leave our headers, which is very, very convenient for us. Okay, so let's go ahead and go to the bottom. All right, so what we see here is that at 1,000 feet, the total mass of the rocket is actually less than the rocket. How's that? It's because we've actually gone negative. We've gone negative fuel remaining, which of course doesn't make sense in the real world. And in fact, if we go up here and we look at where we hit our 0 point, our 0 point's looks like it's going to be somewhere. So it looks like we're only going to make it. So there, where do we go negative? Fuel remaining. We go negative at 227 meters. So it looks like we're only actually going to make it 226 meters into the sky. That's not good for us. So what we want to do is we want to get not only to 1,000 meters, but we want to get to 1,000 meters and have ideally as close to 0 kilograms remaining. All right, so it's very clear to us that 100 has not been the right amount. So let's go ahead and make it 1,000 kilograms. All right, well now, so we find we have 560 kilograms too much, right? We've wasted all this fuel. So the rocket definitely made it, but we've wasted a whole bunch of fuel, carrying fuel that we didn't end up burning. All right, so now we can make kind of a logical statement by going back and forth iteratively here and say, all right, 1,000, I have roughly 560 left. So that says, okay, maybe I need somewhere around the 450, 460 range. Let's go ahead and do that. Let's put in 450 as our starting mass of fuel. There, we're getting closer, right? So now we're only 10.54 kilograms at the top, so let's go ahead and drop it to 440. And what do we find? We find we have 0.54. Okay, let's drop it to, say, 439. Oh, now we go negative. That's interesting. All right, so 440 leaves us with something. All right, so now let's go just see if we can zero in on it. 439.5. Okay, 0.04 kilograms remaining at the top of our launch. I'm willing to accept that. That's almost 0 left, so I think we've done pretty good. In fact, let's just go ahead, just be engineers and be safe to make sure it makes. We're only wasting half a kilogram of fuel, but there you go. So there's our final answer, solved through this sheet with the parameters we've input, which is great. However, what's really cool about this is not only did we solve the problem, but we've actually built a sheet. What if we want to go to 10,000 meters? Let's say 10 meters as our delta. Now if we drag down, whoa, we're nowhere near enough. All right, so now let's go ahead and, well, we're going a lot higher. Let's just go ahead and multiply it by 10 and see what we get, right? Let's go 4,000 kilograms. Ooh, even that's not enough. Let's go 5,000 kilograms. Oh, that's too many. All right, so let's go 460. Right, go back. No, that's not enough. So it's not exactly multiplying by 10. Let's go 480. Nope, not enough. Oh, because I went 480. Sorry, guys. 4,800. All right, sorry, so 400 left. All right, so let's go back down to 4400. All right, now we're about there. So yeah, it's actually. There we go. All right, that's -8. So yeah, we need about 4,400. Okay, so again, what we've done is we've created a program, for lack of a better term, that what this program does is it looks at the amount it requires to raise the rocket a little bit and a little bit and a little bit, and it uses each output to create the new input and then repeat our calculations for us. All right, guys, so that is the spreadsheet that we've created. We've put it back to our original settings, but yeah, that's simply what we've done is we've created our Excel-based program.
Thank you for watching Introduction to Basic Concepts in Engineering. Has this piqued your interest and you want to learn more? Much of the course content and the images in this course are from the text Introduction to Basic Concepts in Engineering for Adept High School Students by Andrew S. Heinz, PhD.
While the textbook is not essential to successfully follow all class videos, it is an excellent resource designed specifically for introducing a student considering engineering to the field and for preparing them for the next steps. It contains many additional topics not presented due to time constraints, as well as additional practice problems and answers. The full text is also available on Amazon. Also, find us on Facebook at SHS Intro to Engineering.